It was not the will of the program to be interrupted. So this is called preemptive, that the operating system preempted the execution of this process. Today we will be discussing CPU scheduling, and this is the area in our course where we discuss the decision making by the operating system to select processes in order to be sent inside the CPU, in order to uh, select to be run in the CPU the next, because of some of the processes either leaving the CPU on their own, or one or more of the processes arriving in the ready queue, so that we may need to decide between the processes that which of them should be sent next to the CPU. The Before we begin the discussion on how the operating system selects a process from the ready queue and dispatches it to the CPU, we need to understand that what is the reason to have that kind of thing in place. The first basic explanation for that would be that there are multiple processes which are running in the operating system, and we want all of them to run concurrently, at least, or sometimes in parallel if we have multi-processor system. So CPU scheduler is there because, number one, we have multiple processes in the operating system. Number two, the processes, all those multiple processes, they need to be run concurrently. Number three, most of these processes need to stay in the CPU for a small amount of time. In other words, their CPU burst is small, right? And CPU burst is the amount of time that we define as the amount of time that a process stays in the CPU. For example, in your code, there were some CPU statements. What are CPU statements? X equal to y plus z, right? Statements like these. And it goes on for a while, and then there is a command in your uh, program which says open file, right? Open file abc.txt, this kind of command. This is an IO command, right? Or IO statement. And this one is a CPU statement. So your programs, every real time every real-time program is a mix of CPU statements and IO statements, right? So every time you have CPU statements, your your program stays in the CPU. But for example, your program looked something like this. So all of the set of these CPU statements is called a CPU burst. The you know Between two IO statements, all the statements inside as a group between two IO statements is called a CPU burst. So this is the amount of time or number of instructions or number of statements that your program wants to stay inside the CPU. Therefore, we call it a CPU burst. And these CPU bursts are really too many inside a program. For example, your program could look something like this, and then there would again be CPU instructions, and then there would again be some IO statements and stuff like that. So here you can see your program, sometimes it goes into CPU, sometimes it goes into IO, sometimes it goes into CPU, sometimes it goes into IO, right? So uh, so this is how your a normal user program looks like. So here we have shown that every program is a mix of CPU bursts and IO bursts. All the time a program takes waiting for its IO is called an IO burst, and all the single group of instructions which lead to a time unit for which program stays in the CPU is called a CPU burst, right? So this would be another reason for the CPU scheduler to exist, is because every program or every process is a mix of CPU and IO bursts. So every time, actually this would be extension of this, every time a process goes into IO burst, some other process can, you know, in other words, when this process goes into IO burst, that means it leaves the CPU. Some other process can be, brought in to the CPU. Another reason could be that there are, or some processes may have higher priority as compared to others. This could be another reason for the CPU scheduler to exist, that the CPU scheduler needs to give more priority to some processes to run in the CPU and less to some others, right? These are all the reasons that can be considered as the reason for the CPU scheduler to exist. Quick question. Okay, so this is another picture where you can see, as I was telling you, that most of these processes have small CPU bursts, right? Because what do we do all the time on our computers? We, you know, try to read data from network, from internet. So our programs are mainly bent towards IO instructions and less towards the CPU instructions. All the browsers, all the, like Netflix or, you know, other things, they are all bent towards having, even the games, but the games are, I think, they're CPU intensive, but all the other programs are mostly network intensive. Even the games nowadays, they have become network intensive, and so most of the programs nowadays are, have small CPU bursts but large, IO bursts. So this graph is a statistical, measure of that. In this graph, you can see that the horizontal axis shows you that there are CPU burst durations. On the vertical axis, you can see how frequently the processes with these CPU bursts exist. So the processes with large CPU bursts are less frequent as compared to processes with small CPU bursts, which are highly frequent. क्या होगा? The benefit for us is that we have a lot to play with, right? We will always have a lot of, uh, you know, uh, processes with small CPU bursts, so we can make very good decisions about how to improve the performance of our operating system, right? So the CPU scheduler is also called a short-term scheduler. We saw that earlier in some other chapter. And CPU scheduling takes place, or the decision taken by CPU scheduler takes place when a process changes the state from running to waiting. That means when a process, it was inside the CPU, it was running, and it executed an instruction, an IO instruction, which forced it to go into waiting state. That it means that your CPU is now free and it does not have any process inside of it. So the CPU scheduler needs to select a process from the ready queue and send it into the CPU. Similarly, this is the second example when CPU scheduler becomes active. it takes a decision. This is when a process leaves the CPU and goes back into the ready queue. So you should remember that this is the time when an interrupt happens, when a process was inside the CPU and the operating system takes it out forcefully out of the CPU and sends it back to the ready queue. This is when again the CPU becomes free, and when the interrupt is finished execution, the interrupt service routine, then we have to take a decision. The operating system needs to take the decision to select a process from the ready queue. Similarly, when a process finishes the IO, the wait for its IO is over, then it goes to the ready queue. So now again the CPU scheduler has to take a decision because the ready queue now has a new process, and that process, the newly coming process which has come out of its IO waiting state, that process could be of high priority, and that means that we need to do something about that, and take a decision that which maybe that newly coming process needs to be sent to the CPU immediately, so the CPU scheduler becomes active. Similarly, when a process leaves the system, it terminates, CPU becomes vacant, and you know the because the CPU is now vacant, the scheduler needs to take a decision to select a new process to send it to CPU. So the first one, okay, so you may have noticed that these two times are the times when the process leaves the CPU uh, with its own will. That means the CPU, the process leaves the CPU voluntarily, because by voluntarily we mean that when a process executes an IO statement, this is the will of the process to do that. The operating system didn't force it to do that. Similarly, when the process finished execution, it was the will of the program to finish execution. The operating system didn't force it to do that in normal circumstances. So these two scenarios are called non-preemptive, right? Whereas these two transitions, you may have noticed that these two transitions, switching from running to ready, when an interrupt happened, it was not the will of the program to be interrupted. So this is called preemptive, that the operating system preempted the execution of this process, and it stopped its normal execution and brought it out of the CPU. And this is involuntary exit of the process from the CPU. Similarly, waiting to ready means that IO completed and the process is now submitted to the ready queue, right? So the completion of IO is also random, and the process has nothing to do with that. The operating system now forcefully brings back the process into the ready queue. It was not the, it was not the doing of the process. So this thing is also called preemptive, that the operating system is doing whatever it is doing when the IO is completed. So these two terms, preemptive and non-preemptive, will be used in the context that whenever we want to say that the operating system is taking action, we will say this is preemptive style. And whenever the process does something on its own and the process is given priority to decide for itself, it will be called non-preemptive. So then there is a certain part of the operating system which is called the dispatcher, and the dispatcher is a small program inside your operating system which is, after the CPU scheduler makes the decision and selects a process, the dispatcher is responsible for sending that process, actually sending that physically sending that process to the CPU. And what are the things the dispatcher needs to do in order to make that happen? It needs to do the context switching, and then it needs to change the user mode, switch the program to user mode, and then it needs to jump to the proper location in the user program to continue its execution from the time it was previously executing. That is the updation of program counter. These are small things, but dispatcher is responsible for doing all of these things, to update the program counter, to fully complete the context switching, and to change the user mode, because there are two modes. One is the privilege mode, one is the user mode. So the CPU scheduler, when the CPU scheduler is active, the program is inactive, and the mode of taking the decision is privileged. And when the program is put into the CPU, now the mode is needs to be changed back to user, because now user program is going to be executed. So dispatcher performs all these things. These are tiny things, but obviously they have significance. But doing all of these things does not count towards the useful time for the user to do the problem solving. So that is called dispatch latency. And this is an overhead, and it is a time taken by the dispatcher to do all these things. And it counts towards overhead, but obviously it's a useful overhead, because we are getting the benefit of multitasking as a result of this program, right? Chale. Then we have the scheduling criteria. So in order to do better CPU scheduling, we need to keep in mind certain things, certain criterias which need to be taken into account every time a decision is made. The first one is CPU utilization. CPU utilization is the amount of time the CPU is kept busy with a process. So CPU utilization would be 100 if the CPU is busy all the time, and CPU utilization is 50 if 50% if half the time is the CPU sits idle doing nothing, and half the time the CPU is busy processing something, right? Throughput is something which is the amount of processes, the number of processes executed per unit time. इसी तरह turnaround time is the amount of the process. Turnaround time is the time taken by a process to finish execution, to finish and we want to minimize this. Similarly, waiting time is the amount of time a process waits in the ready queue. We want to minimize this time. Similarly, response time is the amount of time when a process comes into the ready queue, and when it uh, you know when the CPU scheduler gives a response to it. So we want to minimize this time as well, right? So we want to maximize these two things, and we want to minimize these three things. We want to maximize the utilization and throughput for the CPU. We want to minimize all the times, because all of these times are like waiting times. But the thing is that all out of all of these five criteria, the actual thing that we can measure is the waiting time, because waiting time is the time when a process is submitted into the ready queue, and when it was taken out of the ready queue and sent to the CPU by the OS. So this time can actually be measured with full accuracy, because this is the time, you know, which is in control of the operating system. So we will be measuring these times for different algorithms. So we have different algorithms available to us, which we have, and we come across new algorithms every once in a while. So uh, we will be trying to guess the waiting times for these algorithms, right? So the first algorithm for CPU scheduler is called first comes first served.